All right, welcome everyone. Let's get started. My apologies, I didn't get a printout today. The office closed a few minutes early, and so when I came up on my way to class, it was already closed, and I could see your printouts sitting there, but not pick them up. So I apologize for that. I'll have the stack of them tomorrow if anyone feels like coming by and getting them. I'll hang on to them if you happen to be here on campus. But anyways, today's session number 8 is going to be on hypothesis testing for 2 samples. You have an exam in 1 week, next Monday. I've posted some practice problems for you in the exams areas. I just posted them this afternoon. So feel free to take a look at them, but you're not required to do them. The go-to gold standard for where to see what's going to be on the exam is the lecture notes, and the assignments are meant to assist you also in preparing for the exam. Those are your gold standards. The practice are just for something additional if you would like more practice. There's several questions that are from past exams and other places, and with solutions in a separate document. And then I've added some more problems that are from the textbook, and those ones, the solutions are in the back of your textbook. So please, as you go ahead and do those, feel free to post questions about them on our Google group. And if there is interest, I'm also happy to hold a review session sometime before the exam. I find those are always difficult to schedule at a time when very many people will attend, but I'm willing to give it a shot. And you can also, as usual, book appointments with me through my calendly.com page. So I'm gonna yes.
Before we move on, the format for a test is going to be the same as before?
Yeah, format will be just the same, except without any Blackboard outages, I'm sure. Yeah. No, I'll bring a printout this time just in case. But no, the format will be the same. You'll have the entire 2 hours, 45 minutes if you need it, but my goal will be that you don't need that much time, but that's just so that nobody feels under time pressure. It'll be open book. You can use your textbook, your notes, anything that you prepare and bring beforehand. The only thing that you can also use your own laptop, your own tablet, or whatever if you wish. The only thing really that you're not allowed to do is to be searching on the internet for things during the exam, or to be communicating with other people during the exam. Other than that, it's really, you can use whatever materials you want. All right, so we're going to move on to 2 sample hypothesis tests today, and we'll cover a couple different cases of the independent samples and the paired samples, along with the assumptions required for both of those tests. We'll perform a couple of each of those, the paired and the unpaired tests, and construct confidence intervals in those 2 cases. So let's review first back to the 1 sample case that we covered last week with the hypothesis tests and confidence intervals using the Z distribution, or the standard normal distribution. We were able to use this when either sigma was known or calculated from a very large sample size, so that there is little or no uncertainty in the estimate of the standard deviation for the sample. Then the central limit theorem tells us about the relationship between the population distribution and the sampling distribution. And from that sampling distribution, you can construct confidence intervals, which are a critical value of z times the standard error, which was the standard error was the standard deviation of the we can ignore that because I'm getting sound from here. So the critical value of z tells you where that plus or minus z alpha over 2 is where 95% of the probability is in your sampling distribution, and the standard deviation of the sampling distribution is your standard error, sigma over square root of n. Starting to look kind of familiar, right? Good. And then closely related to the confidence intervals for the one sample case is the hypothesis test, where instead of constructing an interval and potentially making inference based on whether that interval included your hypothesized value under the null hypothesis, you actually calculate a value of z for your sample and then see whether that exceeds a critical value of z, or if you get a p-value from it, whether that p-value is less than your predetermined alpha, your type 1 error rate. These are basic principles that the calculation will change a little bit today, but the principles will remain the same. So when we had to estimate the standard deviation from the sample, instead of knowing what it was, we introduced the t-distribution and said anytime you're estimating standard deviation from the sample, and your sample is less than 300 or 500 or something, you should use the t-distribution. And for very large values, it's just that they're basically the same and you won't notice the difference. But the t-distribution accounts for the additional variability in your test statistic caused by having to estimate the standard deviation from the sample. But other than using a table of the t-distribution instead of the standard normal distribution, the confidence intervals and the hypothesis tests were the same. You need to figure out what your number of degrees of freedom is so that you can look up your value on the t table, but once you've got your value from the t table, you go about it the same way. And this t for alpha over 2 and your number of degrees of freedom is always greater or less than what you get for z. How will t here compare to z for the same value of alpha? Greater. Very good. Yeah, it has wider tails. So it'll be greater or very similar to for a large number of degrees of freedom, but it's always greater than the value of z that we used on the previous page. And similarly, the critical value of t that we use for the hypothesis test will be greater than it would have been for z. So we did hypothesis testing last time for one sample. Let's extend it now to two samples. A couple things are going to be a bit different here. The first is that you need to recognize whether your two samples are paired or unpaired. And that's very important. Unpaired samples or independent samples are exactly that. They're independent. There's no natural pairing of them. So if you talk about taking one sample of cancer cases and another sample of controls who do not have cancer, those are independent samples. They're different people. There's no natural pairing of them. Paired samples are when they are paired. So, for example, the same person before and after a treatment or intervention. We'll have some examples. So here are a couple examples of independent samples. So the birth weights of unrelated boys and girls, they're different people, so they're independent. Laboratory results from 2 different participants in a clinical trial. So if we had, say, one whole set of results that we're comparing to another set of results, maybe it's only a sample size of 1 and you can't really do a hypothesis test, but those are still independent samples because they're from different independent people. Or a comparison of household healthcare costs between the US and Canada. You're going to have to do those with independent samples. Here's some similar but slightly different study designs that are paired. So if we were to look at differences in birth weight of twins, so they're not the same people, but they're 2 members of a twin pair. Those are paired measurements. Pre-post laboratory results for each participant in a clinical trial. So for each participant, you get some observation before their participation, and or say at entry into the study, and then another one at some time later. Those would be paired measurements. Ocular measurements, or measurements of the eye on the left and right eyes of the same subjects, obviously paired. Stress measure scores in twins or husband-wife pairs. So twins, again, it's kind of a dead giveaway. Husband-wife pairs, same thing. There's a pairing to the data. Or measurements from 2 methods of conducting an assay on a patient sample. So in all of these, the pairing kind of implies that you're interested in the difference in before, after, the left and right eye, the 2 twins. You know, there's a strong suggestion that the reason that you're looking at these pairs is because you're really interested in comparing the difference on that paired unit of measurement. All right, so I'll ask a few back to you. Which of these are paired? Number 1, comparing the average heights of males and females. Average heights. Not paired, not based on the information that you have here. Comparing anxiety level of individuals before and after an intervention. Paired, very good. Comparing the anxiety levels of 2 groups, one with and one without the intervention. Non-paired, excellent. If there is this natural pairing, it's not optional that you use the paired test. You must use the paired test because the assumption of independence in your 2-sample independent test is not met. There is the assumption in the unpaired test that you're drawing independent samples from 2 potentially the same or potentially different populations. But as soon as that pairing exists, they are not independent samples, and you must account for that pairing, or your inference may be incorrect. Now, if it's paired, what you do is actually no different almost than what you learned last class. All you need to do is calculate those differences and then use your 1-sample methods. So here was how you calculate Z for 1 sample, and then for paired samples, it's just the same, except we're going to use these D stands for a difference, and delta 0 is the hypothesized difference under the null hypothesis. So it looks both your hypothesis testing and your confidence intervals after you take the differences between your paired measurements Everything else is exactly the same as the one sample case. Sound good? I'll give you a minute to finish jotting notes. Yes? D is your difference between paired measurements. So if we have the left eye and the right eye, we take all of the right eye measurements and subtract all of the left eye measurements. In the example of the twins, there would have to be some kind of ordering of the twins. Maybe we want the firstborn, the values for the firstborn minus the values for the secondborn, for example. Yes?
The null hypothesis would be most cases 0.
The null hypothesis is that the average of the differences in the population is 0. Yeah. So we're doing inference on the differences. And in all of these, so if, I don't know, the husband-wife pairs examples, that your difference could be defined either way. It could be the, the values for the husbands minus the values for the wives, or vice versa, as long as you're consistent about it. So right here. So this is the population mean of the difference under the null hypothesis. So quite often, delta 0 would be 0, but it doesn't have to be. It's your null hypothesis. If for some reason your null hypothesis were that I don't know, if we're talking about weights of husband and wives, maybe your null hypothesis is that difference in weight is the same as the overall population averages in weight for men and women. So in that case, maybe delta 0 is not 0. Any other questions about this? This is defining the paired samples hypothesis test and its equivalence to the one sample hypothesis test. Similarly with the confidence intervals, in the paired case, the calculation is totally equivalent to the one sample case, except that you're working with the differences. So you replace your X bar with a D bar, your average difference, but everything else in that equation looks exactly the same. And then your confidence interval would be around the average difference. Yes?
You have D there, and we can use C and D depending on the case, right?
C and D?
C, I mean the C score or D score depending on the case.
Right, yeah. Right. Yeah, this is just for the t-test where your standard deviation is estimated from the sample. Yeah. Yeah, you can replace those with Z and everything else stays the same. I like how many kind of equivalent formulas there are and all this stuff. So here, let's go through an example, a cell phone study where the question is, does cell phone use while driving impair reaction times? And we're going to go through this with a couple different possible experimental designs. In this one, So we do an experiment where students use a machine that simulates driving situations where there are irregular periods of red and green lights, and then when a light turns red, they need to hit the brake as soon as possible, and that reaction time is the thing that is measured. And in this first design, we have 32 students who are randomly assigned to the cell phone group and 32 to a control group that does not use the cell phone. So is this independent or paired? Independent. Good. Here are the data from this experiment. We calculate, oops, the bars got moved over a little bit, but the mean reaction times in the cell phone group and the control group, 585 and 533. Here's a bar chart of that. So you can see that the mean is a little bit larger for the cell phone group. There's one outlier in the cell phone group. Maybe they had a smartphone and were using, I don't know, Facebook or something. And then the control group. So in the hypothesis test, we're going to want to know whether this difference is enough to provide evidence that the population means are different. So let's write down some of this. We've got a treatment group T and a control group C. Population means mu sub C and mu sub T. And here's our null hypothesis. Either mu C equals mu T or the difference of them equals 0. And notice that our inference is on the difference in means, whereas in the paired case, it'll be on the mean of differences, a little bit different. Right, so this, sorry if that sounds a little too much like a play on words, but here our inference is on the difference in the two means. There's no difference in individuals. So let's go through the test here. The z-score is a little bit different when we calculate it in the two sample case, the z or the t-statistic, but it's pretty close. So it was x bar minus u over the standard error before. Now it's the differences in x bars minus the differences in mu's divided by this pooled standard error. So this thing on the denominator here is just a weighted average of the standard errors from the two. Actually, so it's sigma 2 squared over over n would be the square of the standard deviation for just sample 2, and this thing would be the square of the standard error for just sample 1. You add them and take the square root. And it happens that if you have the same sample size, then this looks just like Pythagoras theorem, the way that they're added here. But you're not probably going to do this too much, but I just want you to see that it's pretty equivalent, the calculation of z. You might have to calculate a z. You'll probably do it in lab tonight. If it's something where you're using t, it looks basically the same, but with s's instead of sigmas. I write unpooled here because in this case we're not assuming the same standard deviation for both samples. That's a decision that you'll have to make when you're doing an independent samples t-test, whether or not to pool the variance or pool the standard deviation. This is the case where we use both of the standard deviations rather than estimating one overall standard deviation. Yes? Why would you not pool them? Yeah, good question. So you have two samples, and why would you pool or not pool the standard deviation between them? One reason why you might not pool them is if they have very different standard deviations. You could imagine that in the cell phone example, perhaps the control group has not very much variability, but the cell phone group has more variability because there's more variety in how people use their cell phones, what they're talking about, what they're doing. So there are cases where the variance can be quite different between your two groups, and if that's the case, then you don't want to pool them. However, if the variance is the same or similar in the two, you will have a more powerful test if you do not pool them, because you get a better estimate of the standard deviation by just calculating it together. And additionally, if you have one very small sample size, or in general, if your sample size is small, it will make more of a difference. But if you have, as an extreme example, 2 or 3 observations in one group and maybe 20 or 30 in the other group, you get a very inaccurate estimation of your standard deviation in that small group. And you can't even estimate whether, you can't even, calculate and see whether they look very similar. So if you had an extremely unbalanced group like that, you probably would want to pool, because you can't reliably estimate the standard deviation in that really small sample. Welcome, thanks for the question. Any others? Yes?
How do you know which, when you get the difference, which one do you know that you should do the subtraction, which one do you know?
So when you subtract, which of your groups or which of your observations do you subtract? That's an excellent question, and the answer is you can do it either way, and it doesn't really matter, other than in your interpretation. So if you decide here to make mu2 the treatment group and mu1 the cell phone group, then from what we saw in that box plot, your differences will be positive. So maybe it'll be a little easier to keep track of, and you would do it that way. But it really doesn't matter. Like, one way you'll get a positive difference in means, the other way you'll get a negative difference in means. But your inference will be the same. Your confidence interval will be different because it has a different interpretation. Like in one case, your confidence interval would be on the increase in reaction time caused by cell phone usage, and in the other case, it would be around the decrease in reaction time caused by cell phone usage. So for interpretability's sake, in this case, I would probably, since we expect and observe the cell phone usage to increase reaction time, I would go cell phone usage minus control group. Thank you, another excellent question. Here it is again with the pooling S1 and S2. I wanted to put it up for you to have it, but I also don't want to get bogged down in equations, and you're going to be allowed to use software on the test. But the only thing I'll point out here is that in this equation, instead of S1 and S2, we have this S pooled. So we're not using separate standard deviations in this calculation of the standard error. And here's your equation for the pooled variance, and it ends up looking a little bit ugly, but all it is a weighted average of your two standard deviations, where they're weighted by the degrees of freedom. So if you have one with, if N2 has twice as many degrees of freedom, and then your sample 1, then it'll be 2/3 your variance on sample 2 and 1/3 your plus 1/3 times your variance on sample 1 divided by that total degrees of freedom. All right, so are you clear on this distinction between pooled and unpooled variances or standard deviations? So getting now finally to your question, the test is more powerful if, and more reliable if the standard deviations are pooled, as long as they should be pooled. So if usually not pooling is a safer assumption, I would say with that exception of when you have one extremely small sample size. If you have one sample size of 2, then you need to pool. Here's a rule of thumb. We like to give you rules of thumb to go back to and not torture yourself over, over how to make the decision, but it's only a rule of thumb. If you calculate your 2 standard deviations and they differ by more than a factor of 2, then maybe you shouldn't pool. And to override the previous one, if either of your sample sizes are less than 5, then you probably should pool. So it's getting back to that small sample size rule. Just a point to note here, if you have pooled standard deviation, you have an integer degrees of freedom, just n1 plus n2 minus 2. If it's unpooled, it's something more complicated. This is called the Welch's t-test, and it's this ugly formula for calculating degrees of freedom, and it's not an integer. So it's kind of weird because you'll see your output from SPSS or whatever, your degrees of freedom is not an integer. It'll be 32.4 or something, just so you know. You can estimate it though if you are happening to do this by hand by the minimum of your 2 sample sizes minus 1. So if you are having to do an unpooled standard deviation t-test by hand, just use this conservative estimate. It'll give you a larger p-value than you would have with the correct number of degrees of freedom. All right, here are 5 steps of the hypothesis test, the independent samples test for the cell phone study. Test statistic of 2.6, we end up with a p-value of 0.011, which if alpha is 0.05 leads us to reject the null and conclude that the mean response time between these 2 groups is different. Now, who can tell me why this is not an ideal design? It took time and money to collect these participants and effort to get them all to come in for this study. Maybe even if they're undergraduates, graduate students, something to come in and you need to put up signs everywhere and wait until you have, it took a while to get 64 participants in the study. How could this have been done more efficiently? Yes. Exactly. Yeah, why not use the same people once while using a cell phone and once without? So it takes a little longer for each person. But potentially you could have had as effective or maybe even a more effective or powerful test with half as many people, just by getting each person to do to do the study or the course twice with and without the cell phone. So let's do it that way. In this alternative design, we have each individual perform the driving task twice, once with, once without the cell phone. Now, if I were doing this, I might want to randomize the order in which each participant does it, or maybe do half where they do the cell phone first and the other half where they do without cell phone first, just so that you're not worried about some confounding with your treatments. Maybe participants start to get bored after a while and stop paying attention regardless of cell phone usage. So we would want to be careful about that in the study design, but this would actually, I think, be a much better study design for the same objective. So in this study, for each individual, and we just do it with 32 here, we get 2 measurements for yes using a cell phone or not, and take the difference. So their reaction time while using the cell phone and without. And on these differences are what we're going to do our one sample test on. So I added here a step 0 just because this is getting a little bit more. There is kind of another step to this whole hypothesis testing routine, which is choosing the right test. So I mean, obviously you have to do that, but I thought I would put it in here just to make sure you remember that it's the first thing that you have to do. You need to choose the right test and assess the assumptions and whether you're meeting the assumptions of that test. So so here the variable is quantitative, so we're going to use the t-test or the z-test. We're going to use the t-test because we'll estimate the standard deviation from the sample. We'll check, we'll make a histogram, we'll see that those differences are approximately normal. That's an assumption of the t-test. And that the data are obtained using a random process, and that we've brought in participants for the study, which we're going to assume to be a random sample from the population of drivers who we're interested in. And to assure this randomness, I think we're also going to randomize the order in which they use the cell phone or do not. Okay, step 1, same thing for alpha. Step 2, now the null hypothesis is on the difference. The null hypothesis will be that the mean of the differences is equal to 0. And the alternative is that the mean of the differences is not equal to 0. And we'll go through the rest of them here. 31 degrees of freedom and -1. And compare this 5.46 to, let's see, what is t here with the confidence level of 95, so t.025, and 31 degrees of freedom, that's about 2.04. In any case, we've exceeded it, so we'll reject the null hypothesis. Probably should have shown this slide earlier, but this would be part of that, your exploratory analysis of the data and checking that the test assumptions hold. You know, no severe skew here, nothing that would lead us to think that the assumption of normality is strongly violated. And one more example from the survey that you all so nicely completed. I wanted to test the null hypothesis that, that Tony and I look the same age. And I did it 2 different ways. Which do you think is correct? The one sample test, which would be the paired design, or the 2 sample independent samples test? Independent? I don't know. Who thinks independent? You want to tell me why?
They're not related. There's no reason to compare.
Okay, so you say they're not related. We're not twins. Okay. Can I have a countervailing opinion? Yeah. Pair each respondent's guess for the 2. Yeah. I think that's right. That's what I would do. I think it's a paired design because it's the same people making guesses for each of us. It's not like I asked half of you to guess my age and the other half to guess Tony's age. Each of you guessed both. So, so there is a natural pairing there. It's the same person making 2 guesses. As it turns out, our inference would be the same. There's pretty clearly a difference in the means. This is our output. Your SPSS output will look a little bit different, but it'll have all these same things in it. It'll have your t-statistic, your number of degrees of freedom, your p-value, your what is your alternative hypothesis, and a confidence interval. So note here that for the one sample or the paired design, we get an estimate of the mean of the differences, which is 19 years. So the average guesses are 19 years older for Tony than for me. With the independent samples design, you get an estimate for the mean of X and the mean of Y. You get separate estimates, and if you were to subtract these, you would get 19.26. So the difference is the same regardless of your design, but it does affect your t-statistic, your number of degrees of freedom, your p-value. Everything else is different. The p-value is more than a factor. Well, no, it's about 4 or 5 times smaller if you were to use the 2 sample test. So in this case, it doesn't matter, but if you were closer around 0.05, that might make a difference. It is a fairly different p-value. Any questions before we're going to change gear again and get out of the how-to mode and talk a little bit bigger picture about hypothesis testing and all that? Yes. If you match people, right? So good question. So you have a design where you have different people, but you're matching them in pairs based on characteristics. So you're trying to say you have, this often comes up when you have a small control or a small treatment group and some very large control group, and you go into this large control group and find a match for each of in your treatment groups. Someone who's maybe the same age, someone, or it can be much more complex than that, who match on a whole bunch of different characteristics. Generally, yes. Like if you're going to match people one-to-one, then you would analyze it that way as well. You would treat those two as a pair and look at the difference. It can be less clear whether that matching really does couple those two people together in cases like that. It depends on how much confounding you have between your matching variables and your outcome. If you had strong confounding between the things you were matching on and your outcome, it would be very important that you keep them paired. And otherwise, it would matter less. Excellent question. Any others? Hurry for time. Doing okay. All right, this is just a little summary table for you to help you pick your two sample procedures depending on whether they're paired or independent samples and whether your variables are continuous or proportions. I want to talk just a little bit about using confidence intervals for two sample the independent case. So for the one sample case, there was easy equivalence between the confidence interval and the hypothesis test. You have one confidence interval. If the null value of your population mean lies inside that confidence interval, then you don't reject the null. If it lies outside your confidence interval, then you do reject the null. In the two sample case for independent samples, you could potentially construct a separate confidence interval for each of those groups. That's generally not very useful. What we actually want to do is to construct a confidence interval on the difference. And the equations I gave you earlier were for a confidence interval on the difference and a hypothesis test on the difference in means. All right, so we're still going after one confidence interval and on the mean difference, not two confidence intervals. Is that clear, that distinction? So in the one sample case, you just have a confidence interval on the mean. In the two sample case, you have a confidence interval on the difference of your two means. All right, and so you have it here in one place, your assumptions for the two sample hypothesis test. I mentioned the assumptions before for the paired case, but in the unpaired case, we have this assumption that these two samples are independent of each other. Whereas for the paired, we assume that the pairs are a unit, but that the units themselves are independent. So your different pairs are sampled independently. We still have the assumption that our population values either the values for the two sample independent case or the differences for the paired case are normally distributed, and that our data are obtained by random sample. All right, I just want to make this somewhat common misconception very explicitly clear on the equivalence between confidence intervals and hypothesis tests for the two sample independent test. The correct way to use a confidence interval to do inference is to get a confidence interval on the differences and reject the null if this if the hypothesized difference in means is outside of that interval. This bottom thing, drawing two confidence intervals and making your decision based on whether they overlap or not, is incorrect, and you'll make the wrong inference by doing that. That's a little bit unintuitive, maybe. Or it's maybe incorrectly intuitive that you should be able to do this thing on the bottom, and it's maybe not intuitive that it's incorrect. Maybe my intuitive explanation of why it is incorrect would be that if, let's say that these two samples are both drawn from the same population, so your null hypothesis is true, if the probability of drawing one sample whose confidence interval, let's say, lies to the left of the mean would be 2.5%, and you'd have another 2.5% that it goes to the right of the mean. So for one of them, that would be 2.5%, and then for the other one to go all the way over to the other side, that's another small probability. So if those are independent samples, those probabilities are going to multiply, and your probability of having non-overlapping confidence intervals will actually be much smaller than 0.05. Does that ring true to everyone? It's like, let me think of another analogy here. I almost have one in terms of taking the subway somewhere, but I'm not sure it quite works out. I guess well, here's kind of a loose analogy, but if you're taking the subway to your destination and there's a variability, you know, let's say a standard error of 5 minutes, so there's 2.5% probability that I'll arrive 5 times 1.96 minutes faster than I was expecting to. Then if you have two people going to that same destination, the probability of those two people arriving, say, 5 minutes apart from each other is not just going to be the same thing as the probability of me arriving 5 minutes different from the mean time that I was expecting. Like, the distribution on those differences in means is different than the distribution of just my arrival time. All right, so you need to build a confidence interval around the difference in means. So significance tests are fun. Everybody in public health does them, but I would be remiss not to leave you with some warnings and limitations of the approaches. Uses and abuses, if you will. The first one is that statistical significance does not equal practical significance. Your p-value relates to evidence against a null hypothesis on your average. So if you have a very small sample size, you can have big differences that are not statistically significant, even potentially a big difference that would be very meaningful, but you don't have enough observations to prove that that difference didn't occur by chance. And then conversely, when you have very large sample sizes, then tiny differences in averages can get very small p-values. There was an example from an article on this very thing that estimated the effect of the minimum bid on eBay camera sales price based on 300 the effect. They used a logarithm of minimum bid. They did a log transformation, got a coefficient of 0.1, standard error of something tiny, a p-value approaching 0. And look at this confidence interval from 0.0990 to 0.1023. So you have a tiny, tiny confidence interval. And what this means is that if you have observed 341,000 camera sales in a random sample, your estimate of the average effect of minimum bid is going to be very accurate. It's if you take another sample of 341,000, that estimate's not going to be very different from what you got the first time. It's a huge sample size. So it's statistically significant, but the question is then, is it practically significant? Is it going to cause you to change your minimum bid when you go to sell a camera? And this is where it's important to write down your findings in the language of what you're interested in, which they did by saying that a 1% increase in the minimum bid is associated with an average 0.09% increase in final price. So, I don't know, maybe that's practically significant, probably not. The p-value cannot be interpreted as the probability that H0 is true. This is a very common misunderstanding of hypothesis tests, and it's a terrible mistake to make. The adage here is that no evidence of difference is not the same thing as evidence of no difference. And keep in mind that the correct interpretation of your p-value is it's the probability of observing your sample or something more extreme if the null hypothesis is true. And you can always get a large p-value just by having a small sample size. So if you have a sample size of 2, you might get a p-value of 0.8. That doesn't say anything about the probability of your null hypothesis being true. The evidence for your null hypothesis, which we've just talked about, we're not actually calculating it yet, but that is the power. The power being your probability of rejecting the null hypothesis if the null hypothesis is false. Third one around your choice of alpha, the type 1 error rate. So that's a common cutoff, but do keep in mind that it's an arbitrary choice. So if we have, let's say, a study that chose 2 primary endpoints that are fairly closely related to each other, and we get a p-value of 0.055 for one of those endpoints and 0.04 for the other endpoint. It's support for the alternative hypothesis in both cases. If you're being strict about your alpha, then you would not reject your p-value in the or you would not reject the null from the p-value of 0.055, but you should keep in mind that even though you didn't have quite enough evidence to reject the null there, on the balance of things, the null is still probably false, and the evidence is very similar for these 2 endpoints. Oh, this is a good one. Forgetting that significant tests are about central tendency of the population, and they're not about individuals. So significance tests are all about the central tendency of a population, whether the average in your population is the same or significantly different from that under your null hypothesis. Here's an example that was on a previous year's exam that like more than half the class got wrong, so I put it into the lecture to try and hammer the home. In a random sample of 100 children, they find a mean serum level of 5 micrograms per deciliter, which is less than the normal limit of 10. So does this mean, and they get a p-value of 0.01, does this mean that fewer than 1% of children have serum levels exceeding the limit? No. I feel bad for maybe confusing you by even putting that up on the board, but that's totally wrong. The p-value is the probability of observing this difference if, in fact, there is no difference in the means. Another misinterpretation of this might be around confidence intervals. If you construct a confidence interval, 95% confidence interval, and find that that confidence interval goes from 3 to 7 micrograms, does that mean that 95% of individuals have a serum blood level between 3 and 7? No, that's the sampling distribution. That means that 95% of your samples of that size would have a mean between 3 and 7. And it's the interval within which you're 95% confident that the true mean lies. Assuming that because n is small, you cannot believe any results of a significant test, or conversely, that because n is very large, the results must be true. Keep in mind that the statistical tests that you've learned, they all account for sample size in their calculation of a p-value. So as long as your assumption of the random sample and a representative sample is correct, you can rely on your p-value regardless of what the sample size is. If you have a biased sample for some reason, then whether it's small or whether it's in the millions, your hypothesis test cannot necessarily be believed because it's not representative of the population that you want to do inference on. So representativeness is important. Sample size is important too, but it doesn't mean that a small representative sample can be very valuable and that's not a reason not to believe the p-value. And skepticism, statistical analysis, what you'll all be doing, cannot remedy basic flaws in producing the data, such as voluntary response samples when you go put up signs and wait to see who replies to them, uncontrolled experiments, and measurement bias. This study here made it onto the front page of the Times. It was a cancer study that I was very familiar with that claimed to be able to predict whether people would respond to chemotherapy or not based on their gene expression. And based on everything that they presented, it looked like they could do that. But what they hadn't mentioned in the paper was that they had taken all of their chemosensitive group and measured them in one batch, and all of their chemo-resistant group and measured them in another batch. So there was systematic bias in the measurements between their cases and their controls. And it's the most basic element of experimental design. It's the same thing whether you were doing interviewers. You wouldn't have one interviewer interview your control group and then different interview all of your case group. It's randomization in the design of your study is key, and if you don't do that, it doesn't matter what you do statistically. Oh yeah, tests can be statistically significant by chance. We're talking about probabilities here, so even though you choose to reject your null hypothesis and your p-value says that you should have, you could still be wrong just by chance. And furthermore, if you do tests over and over again, your chances of making that type 1 error increase. So here's an excerpt, an excerpt from my favorite comic book, XKCD, where scientists have discovered that which one is it? Green jelly beans cause acne after they had tested, let's see, purple, brown, pink. They tested all these ones and got p-values greater than 0.05, but for green it was less than 0.05. So green jelly beans cause acne. True effects may not be as large as the initial estimates, and one of the big reasons that this happens is publication bias. And I can tell you that when you do a study and you find that there's no difference between your cases and controls, or you can't reject your null hypothesis, whatever it is, it can be harder to publish it. And it's more likely just to sit there and never get published. And that is kind of an extension of the green jelly bean problem of different groups trying the same thing or similar things until someone finds a statistically significant difference, and then they report that. But there's likely, when that happens, it is likely to be a biased finding, potentially through no fault whatsoever of those researchers, just because they were the group that drew the random sample with a larger difference, and so it was easier for them to get published. There are also cases where this has been done intentionally. A famous one being this reboxetine, which was an antidepressive manufactured by Pfizer, where there were a number of null findings and that were not published, and the sort of stronger findings were published. And so the effect of it was still there, as found in a meta-analysis later that included unpublished findings. It was just much weaker than initially reported. And this is why the Food and Drug Administration and some journals now require registration of clinical trials. So if you want to have an FDA-approved trial, or if you want FDA approval for a drug, your trial must be registered before you start it, or else they will not consider it as evidence. But when it comes to other things that aren't FDA approved, there's no way of knowing. All right, and that's all I have for today. Boy, we went a little over time. Sorry about that. I will see you all downstairs.